Okay, so we are going to start talking about waves, properties of waves, things like that. The good news is we use a lot of the same terminology that we've been using in the simple harmonic motion part of this unit. Okay, so we're still going to use terms like frequency, period, okay, amplitude, okay, all of that kind of stuff. Those are all still going to be terms that apply here, right? The reason being is in order to get waves, there has to be something that is disturbing a medium and oscillating with simple harmonic motion. Okay? There has to be something that creates the wave. Right? Everyone with me so far? Okay. Is a wave matter? Exactly. A wave is not matter. A wave is energy. Okay? It's a traveling disturbance. However, with the exception of light, all waves require a, what you called it, a material to travel in, right? Yeah. Yeah. We have actually a term for that. It's called a medium. Okay? All waves, except for light, okay, must have a medium in which they propagate. So right now, you hear me because my sound waves are propagating through the air. The air is a medium. It's not a great medium for traveling, for conducting waves, but it works good enough for our purposes. Okay? Water. Is water a better medium for conducting waves? That's why you see a lot more waves in the ocean. Okay? There's lots of ability of water. Okay? And even solids can conduct certain kinds of waves. Some waves better than others. All right? But waves have to have a medium in which to travel. It's why in space no one can hear you scream. One, because you'd pop, because you'd be in a vacuum screaming. Okay? And secondly, because there's nothing there for you to disturb. Okay? So if you're an astronaut, you're out in space in your spacesuit, and your radio is dead, okay? And you're screaming at the top of your lungs, your crewmates can't hear you. Okay? If your radio was working, it would transmit light waves, okay, electromagnetic waves, radio waves, through the vacuum of space to them. And they would receive it and they would hear it. Okay? But if you're just screaming, they can't hear it. Now, when they get close to you, is there a way they could hear you? What could they do that would allow them to hear the sound you're making? Well, you seem like you have an idea. Touch space plates together? Absolutely. Okay? If one person is trying to talk, but the radio's not working, if you put the faceplates together, the sound will cause the faceplate of the first person who's talking to vibrate. That will travel through to the second person's faceplate, which will vibrate and cause the air inside their helmet to vibrate, and then you will hear the sound. If it's screaming, they're probably not going to hold their face next to you for very long. Okay? They're probably going to push you away and go, shut up, I'm right here. Okay? And then they'll put it back closer to you, and they'll be able to hear you. In the same way that a tin can phone works. Anyone ever have one of those as a kid? I'm kind of starting to see less and less people doing that because what is a cell phone? Okay, it's ruined your childhood. Okay, you needed to make a tin can phone at some point in your life. So you have two soup cans, okay, and you drill a little hole in the bottom, and you tie a string in between them. Okay, as long as that string is tight, you can talk into one, and the person at the other end they can hear you because your waves hit the bottom of the can, which oscillates at the same frequency you're speaking at. That gets transferred to the string, which will transport it to the other end of the tin can phone. Okay, that end will vibrate and you'll hear it. Same as putting a glass up against the door. Okay, the glass then picks up the vibration of the door. The air inside the glass begins to transmit the sound, and you hear it through the glass. Okay, so all of that stuff works because these are all media that sound can travel through, that waves can travel through. Okay. Everyone all right with that idea? Okay. So waves can be good, waves can be bad. It depends what they're traveling in. Okay? Most of the time, waves traveling through water are pretty harmless. Is there a time when they're not? What kind of waves are those? Yeah, tsunamis, tidal waves. Okay. What usually causes that? Earthquakes, yeah. Okay, to make a tsunami, at least like along a fault line, there has to be the right kind of earthquake. If it's a slip like this horizontally, it doesn't usually cause a very big wave. Okay, but if you have a plate boundary where one plate's trying to go underneath another, it's called subduction. Okay, you probably learned that in grade 8 when you learned about faults in Earth and stuff. Okay, the one plate will try to go under the other. Well, it pushes on it. Sometimes that plate that's still on top will snap. Okay, and when it snaps back, all this water is above it. Boom, you just got all this force that just suddenly lifts all this water up, and that energy travels away. Okay, it's not a big deal out in the middle of the ocean. A tidal wave out in the middle of the ocean isn't all that big, or at least high. Okay? But when it gets closer to the shore, it gets bigger. How's that possible? Wouldn't it getting bigger means it have more energy?
It rises as it goes along the bottom, right?
As it goes along the bottom, and what does the bottom do? It gets shallower.
Yeah.
Okay. Here's why energy is actually conserved in a tidal wave. Because otherwise, if you think about it, if the wave's only this tall and it's heading towards the shore, you're like, well, it has a certain amount of energy. It's going x fast and it's x high, and it has a certain amount of kinetic and potential energy. Okay. But as it approaches the shore, it slows down. Okay. The depth of the water can change the speed at which the wave can travel. Right? So the front of the wave slows down before the back of the wave, right? And as that happens, the front of the wave slows down, the back of the wave catches up, and it just forces the water upwards. So you get this much, much taller wave as you get closer to the shore.
Would the fault lines be like building up elastic potentially?
Yes, to an extent, yeah. I mean, it's hard to think of rocks like building up elastic potential energy. You got to remember, as they're sliding underneath, it's pretty hot too, right? There's all kinds of deformation in the crust. Okay, it's more that maybe the one forces its way under and radically lifts the other one. Okay, but we always diagram it and model it as an elastic snapping action, kind of upwards. Okay, so we're going to learn the characteristics of the two types of waves that we're going to talk about. Okay, transverse waves and longitudinal waves. I did not spell that wrong. Okay, longitudinal is a type of wave. Longitudinal are lines on a map. Okay, they're two different things. Okay, but I get a lot of people going, could you spell that wrong? Okay, longitudinal is a type of wave. Okay, and they work differently, okay, in terms of how they propagate. All right, so a transverse wave is the one you see. Okay, like you've seen a water wave, okay, it's going like this, that's a transverse wave. Sound is actually a longitudinal wave. It's a series of compressions and rarefactions. Okay, think about if you've ever seen a subwoofer, okay, when it's making noise, okay, and it's vibrating back and forth like this. When it goes in, it's actually creating an area of air that is less dense because it's pulling away and creating a low pressure area. And then it follows that with a move rapidly forwards, which does what to the air? Compresses it. So you've got an area of compression, an area of rarefaction, compression and rarefaction, okay, that travel outwards. And that change in pressure when it strikes your eardrum makes it go in and out. Okay? The compression forces your eardrum in. The rarefaction, which is lower pressure, pulls it back out. When it vibrates back and forth, that's how we interpret sound. Okay? So all of that still involves energy. Okay? Waves are carrying energy. They're using the medium to do that. Okay? All right. All right, so a wave is a traveling disturbance. Okay, that's really the definition of a wave. It is a traveling disturbance. In order to get a wave, you have to disturb a medium of some kind. Okay, so in the diagram there, okay, we've got this motorboat passing a fisherman in just like a paddle boat. Okay. As the motorboat goes through the water, it pushes some of the water down, it pushes some of the water out, okay? It creates a disturbance. That disturbance travels away, okay, as a wave, right? How do I know, if I'm the fisherman, that that wave is carrying energy? What does it do to the fisherman's boat? Yeah, it rocks it. It actually lifts it up, right? When the crest, that's the upward part of the wave, meets the boat, it's going to physically lift the boat. Does that require work? Okay, well then there's a change in energy. The energy comes from the wave. Okay? It transfers its energy to the boat. Okay? And obviously that'll keep happening. Now, this is a weird thing. How many times did the boat disturb the water? Why is there more than one wave? Same thing happens with a rock, right? You throw a rock into the water and you get like a whole bunch of waves, but the rock only went in one time.
It's disturbing like different parts of it every time.
Yeah, as it travels through, for sure, yeah, that disturbance would be longer, but it's not so much multiple disturbances.
Was it like the high pressure, low pressure thing you're talking about?
Kind of, yeah. Okay. Is water a polar molecule? Does it create bonds with itself? So if you push it down, okay, is it going to pull down on surrounding water molecules? Okay, when those come back up, okay, is it going to stop it when it gets to a certain point and then have it come back down again? Okay, like if you ever watch a splash in slow motion, right, you see it go in, you see the water go down, and then you actually see the water do this for a little while. The water, because it's a polar molecule, actually acts almost like an elastic material and oscillates up and down until the disturbance is completely worn out. Okay, so we see multiple waves going away because the water is oscillating with simple harmonic motion. Okay. All right, so waves of traveling disturbance. Okay, definitely got to know that. That's an important little detail there. Okay, and waves require a medium, so some matter of some kind in which to propagate. Some materials propagate waves better than others. Okay, some materials propagate different types of waves better than others. Okay, for transverse waves, like water waves, okay, the less dense a material is, typically the better the wave will travel. Okay. For a longitudinal wave, which is a compression and a rarefaction, they actually travel very poorly in low density materials, but very well in high density materials. Okay? To give you an example, for sound, okay, sound in air travels at around 330 meters per second. Sound travels in water at 1,560 meters per second. Okay, you put it in a solid material, and depending on the solid, that could be 3,000 meters per second. Okay, the closer together the material is, the more dense it is, the better those compressions and rarefactions can travel through it. But it's really hard to cause a transverse up and down wave to travel through a wall, right? Thankfully, because that would be really bad. Okay, when walls start to do this, bad things happen. Okay, in fact, I was actually just talking to Mr. Dickey about something that I saw this weekend. I was in New York on the weekend, and they have the really, really tall skyscrapers there. Like, they make the ones in downtown Calgary look short. Okay, like the tallest one in downtown Calgary would go about halfway up, and it's ridiculous how tall these buildings are. They have this. The reason that they're not tall in Calgary is because we get so much wind. Okay, buildings will actually sway back and forth. In downtown Calgary, the buildings are shorter, they don't sway quite as much, but if you're sensitive to it, you can detect it. Like, you might have to go home from work because you get seasick at your desk, okay, if you're near the top of a taller building. In New York, okay, they actually have two buildings on what they call Billionaires Row, where the penthouse apartments can't be sold. No one will buy them. Part of it is they're $126 million. Not a lot of people have that kind of money to blow on a penthouse apartment, okay? But also because they can sway back and forth 7 to 8 feet in a strong wind. They actually have to shut the elevators down because the elevators would get stuck in the shafts as they're going back and forth like this, okay? So in a strong wind, you can't even get to your apartment unless you take the stairs. And nobody is going up to the top of one of these things on the stairs. Okay, unless they want to lose about 20 pounds on the way up, because it will be a lot of stairs. Okay, so if you get a wave traveling back and forth in a building, that's probably not good, right? We're going to talk a little bit more about that when we talk about resonance, because there are lots of instances where buildings are designed to tolerate that and not fall over, and instances where we didn't do such a good job of that, and they did. Okay, so we'll talk about a bit more of that when we talk about standing waves. But absolutely, waves can travel through pretty much anything. Sometimes it's harmless, and sometimes it isn't. All right, so a wave, okay, is not a bulk movement of water. Okay, this is something that people kind of don't always get right away. if waves, if when a wave travels in the ocean towards the shore, okay, does the wave go towards the shore or the water go towards the shore? When a wave travels through the water, what does the water actually do? It just goes up and down. Okay? If you were to track individual water molecules as waves traveled through the ocean, all they would do is go mostly up and down. There's sometimes a little rotational action that happens there, okay? But they don't move from point A to point B. Not like a river. Okay? In a river, if you tracked a molecule of water, you'd watch it go downstream. Okay? But in the ocean, it would simply oscillate. Because think about this. If the water did what the waves are doing, which is traveling from point A to point B, then all the ocean would end up on the land. And there'd be a big hole in the middle of the ocean because all the water always seems to go towards the shore. Okay? So obviously in the ocean, okay, and in all water waves, the water, which is the medium, simply oscillates up and down. It is the wave that travels from point A to point B. The energy is traveling through the medium, and as it travels through the medium, it disturbs it in the direction that it is oscillating, up and down. Okay? Or if we're talking about sound, back and forth.
What causes the wave to move?
What causes the wave? Most waves on the ocean are what we call wind-driven waves. So wind traveling near the surface causes a slight rotation in the water. Then that creates the wave which then travel away. That's often also why, as waves approach the shore, you see them curl. It's because the motion isn't purely up and down. There's a bit of a rotation that goes in there that can cause that curling effect that surfers love, right? They like to get inside the curl of the wave. Okay, so it's important to know that a wave does move, but the medium only oscillates. Okay, it's important to know that the direction of the wave is traveling is not going to carry the medium with it. It'll cause the medium to oscillate, but the medium won't go from A to B. Okay? So if that's the case, if the medium, the water, let's say we got a big tidal wave. Okay? Big tidal wave's coming towards the shore. Okay? Everybody's running away. Why? The water is just going to go up and down. Why is a tidal wave such a huge natural disaster that ends up putting water way inland? If I hold a bucket of water over my head and dump it out, does the water stay where I drop it? It splashes, right? That's what happens with a tidal wave. Okay? As the wave approaches the shore, it gets really slow and really tall, and then the wave runs out of water. So where does it go? It actually goes into the air. Okay? It travels out of the water and into the air. If you were standing on the shore, not a good idea by the way, when a tidal wave was coming in, okay, as the tidal wave reared up, you'd actually feel a gust of wind, okay, as the wave energy leaves the water and moves into the air. And you would feel this big gust of wind. Okay? If it was like one from a giant meteor or something like that that hit the earth, there'd be almost a shock wave. Okay, as a result of that tidal wave, because the tidal wave would move through the ocean faster than sound. Okay, yeah, it'd be pretty crazy. So what happens is that wave is disturbed way, way, way up, and then all of a sudden the energy that had disturbed it and held it there leaves. It just takes off and goes into the air, and now there's nothing to support this giant column of water. So it just falls. It's been given all this potential energy. It just falls back down because of gravity and splashes inland. Okay, that's what inundates the coastal areas. It's essentially the splash. Okay, it's this wave energy that's been disturbed, but it's not the ocean reaching in and just pulling everything in. Okay, it's really just the wave no longer supporting the water. All right, so first kind of wave we're going to talk about are transverse waves. Okay, so transverse is another way of saying perpendicular. All right, we call a transverse wave transverse because the direction the wave travels is perpendicular to the oscillation of the medium it's traveling through. So a water wave is a transverse wave. So water oscillates up and down, but the wave travels horizontally. Okay, that's a transverse wave. Those are the ones that we can see. You don't really see transverse waves. Okay, or sorry, longitudinal waves. They're not something we can really perceive compression-wise. Okay, so a transverse wave, the wave travels horizontally, the oscillation is 90 degrees to that. Okay? Okay, so in a transverse wave, okay, the wave is traveling from left to right, okay, but the disturbance is up and down, perpendicular or transverse. Okay, so like I said, transverse wave is one in which the disturbance is perpendicular to the direction of travel of the wave. Now, we got to look at the parts of a wave. Okay, some terminology stuff here, right? The maximum distance that the medium is disturbed from equilibrium is still described with the same term we used for a mass on a spring or a pendulum. The maximum distance anything gets from its equilibrium position is its amplitude. Okay? Amplitude is one of the main measures of a wave's energy. Okay? The greater the amplitude, the more energy the wave will have. And obviously, the faster the wave is moving also affects its kinetic energy, but we're going to see later that basically waves only have one speed that they can travel in any given medium, so that number is kind of fixed no matter how big the wave happens to be. Okay? Now, other terms here. For a transverse wave, the highest part of the wave above equilibrium is called a crest. Okay? The lowest point below equilibrium is called a trough. Because it looks like what livestock eat at. Okay? Okay. The equilibrium position is still the same term. It's the undisturbed position of the medium.
Would there still be a trough that was above if like the wave never went before below the equilibrium? Actually, that one.
It couldn't happen. I mean, you could have a pulse. If we have a pulse, we don't have a complete wave. We just have either a crest or a trough. Okay. So in that case, we just call it an up pulse or a down pulse. For a wave to have a crest and a trough, we have to have a complete oscillation. Okay, now, this is a new term here, okay? Wavelength. We can actually measure the physical length of one oscillation of a wave. Okay, so if I start here at the crest, the wavelength is how long the wave is before I get to the next equal spot on the wave. Okay, so one wavelength is the distance, and I'm going to show you something kind of funky here. Okay, is the distance between any two equal successive points on a wave. All right, so it is the distance between the first crest and the next crest. Okay, it is also the distance between one trough and the next trough. Okay? It is the distance between any two equal equilibrium positions. Okay, why did I put in the word equal? Because there's an equilibrium position right in the middle of this wave. Okay? But is it the same as this equilibrium position? No. In this equilibrium position, the medium is moving up, but in this one, the medium is moving down. So they're not successive points. The next successive point is the one that's the same. Okay? So in fact, you could do this. Any two equal successive points on a wave are always going to be exactly one wavelength apart. Okay? It doesn't matter which two I pick. Okay? Everyone all right with that idea? So wavelength is going to be measured in meters. Okay? Because it's a length. Okay? Length is always measured in meters. We use this weird little symbol to represent wavelength. Anyone know what that symbol is? Anyone familiar with their Greek alphabet? This is the Greek letter lambda. Okay? And it's the Greek letter L for length. Okay? So lambda, okay, is technically drawn this way with a little kind of angled line and then this line that has these two curves on it. For the sake of time, we just draw lambda like this. Okay? It's a short stick holding up a longer stick. Okay? So lambda represents wavelength because it's the Greek letter L, okay? Because we already use L for length. So we can't use it again. So we borrow letters from the Greeks. How long would it take for the wave to complete its oscillation from here to here? What would I call that?
Period.
The wave's period. Okay? The number of waves that go by me every second would be the frequency of the wave. So all these terms overlap. Okay? All the terms we learned in the first part of the unit still overlap. We still use them. They still mean the same thing. Okay? So we've got amplitude, we've got crests and troughs, we've got the equilibrium position, okay, we got wavelength represented by lambda, period, frequency, okay, all that stuff still stays the same. Okay, so longitudinal waves are, the oscillation of the medium is parallel now to the direction the wave travels. Okay, so right now as I speak, my vocal cords, okay, go back and forth like this, compressing and rarefying the air, okay, producing sound waves. So the sound waves are doing this, and the waves are traveling in the same direction. So the direction of the oscillation and the direction of travel are now parallel. Okay, so this is a compression, and this is a rarefaction. Okay, so in the diagram here, you can see that the oscillation, if I was to watch any one spot on that spring, I would only ever see it go back and forth. I'm going to show you this. I'm going to bring out our extra long super science slinkies. Okay, and I'm going to show you what these waves look like on those. Okay, so we've got our oscillation back and forth, but the wave is traveling parallel to it now instead of perpendicular. That's the only difference. Everything else mechanically about transverse and longitudinal waves is the same. Wavelength, period, all that kind of stuff still applies the same way. Okay. Okay. So yeah, you guys, in your life, you've only ever probably had the plastic kind of slinkies because metal slinkies were dangerous. We had dangerous toys when I was a kid. Now looking back, we also had lame toys. That's what we had. And you just watch it go down the stairs. Right? It even had its own little song in the ad, which I won't subject you to because it will get stuck in your head. Maybe another day I'll do that. Okay, so you can see there that this is essentially what we saw, right? We saw the compressed area, okay, the compression. You can see that there's kind of a transition from very compressed, okay, to rarefied. You can see that this part is stretched, this part is stretched. There's a little bit of a transition there between compressed and stretched. Okay, but it's going back and forth. If you see in this diagram, it's kind of got the same part of the spring marked, just like we did with the red tape. And all that marked part of the spring does is oscillate back and forth. Okay, but we can see a compression come in here, and we can track that compression as it goes through. That does travel through the spring from one end to the other. Okay, but each individual part of the spring just oscillates back and forth with simple harmonic motion. Okay? Everybody all right with that idea? Okay. Okay, actually, I was going to show you the 2 videos that we had here to do with waves. Okay, so the big worry obviously with water waves, ocean-going waves, okay, is that they do change speed when they get close to the shore because their depth changes. Not that they're not traveling in water anymore, but the depth of the water changes the properties of the water, and thus it changes the speed of the wave. So they get taller because they get slower. They have to conserve their energy, okay? So it turns into potential energy of the wave height and then crashes down. Okay, so both transverse and longitudinal waves, as we said, are examples of periodic waves. They consist of patterns that are produced over and over again by something experiencing simple harmonic motion. So that one video showed the little dipper that was going up and down into the water, okay? That's just that's oscillating with simple harmonic motion. If you've ever been to a wave pool, okay, like the one they have at West Edmonton Mall, okay? I don't know if you've seen how that works, but the floor underneath the thing just actually goes up and down and just keeps producing the waves, okay? It's just oscillating up and down with simple harmonic motion to produce the waves in the wave pool. Okay, so we talked about this a minute ago, okay? The length of one complete cycle of a wave doesn't, as long as it's 2 equal points, it's a complete cycle. That's the wavelength denoted by lambda. The amount of time that takes to go by is the period. The number of times one of those goes by in a second is the frequency. Okay, and then obviously how fast they're going is the speed of the wave. We've got our amplitudes here. The amplitudes occur at the trough and the crest, okay, of the wave. Okay. All right, so as we said, amplitude still the maximum excursion of a particle, okay, in the medium or of the medium from the particle's undisturbed position. So flat water to the crest or trough of a wave, okay. The amplitude is the distance between a crest, highest point, or trough, lowest point, okay, on that wave, okay. And the bigger that is, the more energy that wave will have, okay. And we know this because if I want to make something, a sound, let's say, louder, I need to use a what? An amplifier. Okay, what does an amplifier do? It makes the speaker move more, not faster. Okay, faster would be the frequency it's producing. Okay, but makes it move further away and from its equilibrium position in either direction. Okay, the further it moves, the greater the amplitude of the waves, the louder we perceive them to be. Okay, now, can large amplitude waves be harmful to you? They can. What do we measure the amplitude of a wave in for sound? What are the units for loudness? Decibels. Okay? What decibel level causes permanent hearing damage? It's 90. Anything over 90 is going to start causing permanent hearing damage. You ever had the sensation you take your earbuds out and all of a sudden you feel like this pressure change, almost sounds like water rushing into your ear? Feel a little pressure on the eardrum? Okay, that's, you've had your earbuds up too loud. Okay, that you're at 90 decibels. Now, more of the modern ones that come with your, like if you have your phone, the ones that Apple provides, there's usually a safeguard that won't let you go over 90 unless you like deliberately change the settings. But if you got, big Beats or something like that, hey, obviously you can make them louder than that. We had a kid here years ago, probably 15, 20 years ago. He's got to be deaf now. Okay, like he would walk down this hallway and I could hear what he was listening to, and it was always horrible, like cursing and swearing because you could hear everything. Okay, his headphones were so loud. Okay, we could hear him when he was in the atrium, okay, walking towards us. Okay, dude's got to be deaf now because his eardrum had to be just going like this, okay, nearly destroying anything. Okay, so what is it that causes the hearing damage? I mean, if you perforate your eardrum, that's one thing, but usually you have to have a pretty loud sound, like over 120 decibels will perforate the eardrum. Okay, that means to tear it. What usually causes the damage?
Does it have to do with the hairs within your
It can. Some hearing damage, yes, can be the nerve endings in those little hair cells that are in the cochlea. Okay, but if you've ever had ringing in your ears, anyone had that sensation before? Like you went to a concert or a Flames game and they actually scored and they were, the big horn went. Sorry, I couldn't resist that one. They were playing so well for so long. So they, when that horn goes off, it's like 100 to 112 decibels. It's really loud. If you're at a concert, it's definitely over 100 decibels. Okay, the next day your ears are ringing. Okay, well, that ringing sound is actually the result of swelling in your middle ear. What's attached to your eardrum? Bio people should know this. There's 3 little bones. You remember what they are? You actually learned it in junior high too.
Isn't it like ossicles or something?
The ossicles, you remember what the names are?
Took us like a year ago.
The malleus, the incus, and the stapes. The hammer, the anvil, and the stirrup. Okay, are the 3 bones in the middle ear. Those bones are attached to each other by ligaments. There's cartilage there, just like any other joint in your body, your knee, your shoulder, your wrist. Okay, joints are all the same. Well, when your eardrum moves a lot further than it's supposed to, it isn't any different than if you make any other joint in your body move further than it's supposed to. What do we call it? Could be a dislocation. That's quite a bit more serious than what I was thinking. It starts with S. A sprain. Okay, so essentially what you're doing with those tiny little bones and their tiny little connective tissue is you're straining them, okay, past where they're supposed to really go. And the natural reaction in any joint that's been strained or sprained is to swell. So you get inflammation in there, and if you've ever had a sprained ankle or a knee or something like that, it feels weak for a while, right? It kind of moves on its own a little bit because it doesn't have the same support because of all the swelling. The same is true in your ear. So any movement of your head causes those bones to move. Well, those bones are connected to your auditory nerve, and it tells your brain that you're hearing things. That sound's not really there, the ringing in your ears, okay? But it's the result of the swelling on those little joints. So every time you hear that, every time your ears ring, you've caused permanent hearing damage. Okay? Now, I'm not saying that I went to a concert and now I can't hear anything. It doesn't work like that. Okay? But it's gradual. It's like anything else. Take it from someone who's got like arthritis. Okay? I have basically no cartilage left in my right knee, very little healthy stuff left in my left. Okay? It's the price you pay for athletic prowess in your youth. All right? You guys hopefully won't have that problem. But what happens as that stuff deteriorates is you get a buildup of scar tissue. Okay? And that scar tissue limits the mobility of your joints, which means those little bones don't vibrate the way they used to. Their mobility is now limited. So you start to lose your hearing at either end of the kind of spectrum of hearing. Okay? You would start to lose your ability to hear the really low frequency sounds and the really high frequency sounds. Okay? They usually detect hearing loss because you're struggling to hear the soft letters, S's, F's, T's, okay? Things that are soft sounding. Those are the sounds you lose first. They're the highest frequencies, okay? So you'll start to notice that you're having trouble understanding conversations, hearing everything. That's the result of slow buildup of that hearing loss.
So is tinnitus cause hearing loss?
Tinnitus is, yeah, it's the inflammation, it's the swelling, yeah, and it does. And it's also been linked now to things like dementia and things like that because the overstimulation of the nerves is causing something to go on in the brain. There's a whole bunch of research around that right now about tinnitus and its relationship to Alzheimer's and dementia. Yeah. Okay. All right. So is that part making sense there? Okay. So be mindful how loud you listen to your headphones because your generation is going to have the most hearing loss. Okay, of really like any generation that's ever been, because you have had access to portable electronics far more than any generation before you. Okay, and you guys have your headphones in a lot, and most of them cover completely and seal. Okay, or they go in the ears and they seal and they don't allow the pressure to equalize as much. Okay, and so it's more than likely you guys will have the most hearing problems of any generation before you. So don't listen to it so loud. You want to hear your children laugh. It's a beautiful sound. Okay? I mean, I'm not going to have kids. Well, if you do end up having kids, you want to hear them laugh. It's the best sound in the world. Okay? You don't want to sacrifice that to listen to Taylor Swift. Okay? Or whatever. Okay, wavelength. So just quick definitions here, guys. Wavelength is the horizontal length of one cycle. We use lambda for that. Okay? Any two equal successive points between or on the wave. Okay, period, time for one cycle, okay, or the time for one wave to pass an observer. Okay, frequency is the number of cycles per second, or 1 over t, okay, all stuff we've talked about before. Okay, and then for any wave, there's essentially three properties we're most concerned with: the speed of the wave, okay, the frequency or period of the wave, and the wave's wavelength. Okay, this is what we're going to talk about tomorrow. It's the universal wave equation. It relates the speed of a wave to the wave's frequency and its wavelength. Okay, it can tell us a bit about what the behavior of the wave is going to be like when the speed or frequency or wavelength, okay, of a sound or whatever is changed. All right, so that is what we will head to tomorrow. Okay. Now, just to show you something here, okay, this whole relationship between simple harmonic motion and waves. If I have a mass on a spring oscillating up and down, what pattern does it make? It makes a wave. Okay? All things oscillating with simple harmonic motion have the potential at least to produce waves. All right, I think that's all we got for today. Hey, remember, if you want to hand in that simple harmonic motion assignment to me early, I will take it. Okay? And both of those assignments are due after Christmas. I believe the 8th and the 9th is what I made them do, right? So make sure you get those done before Christmas so you don't have to do them early.
Just in case I wrote that down.
I originally had planned for that, but I'm feeling like I might not. We just did the assignment on simple harmonic motion, so I feel like I get it done. So, okay, I'm making the executive decision. You can thank Quill. Okay? She helped me make the executive decision. No quiz. Right. We're going to try and gain us another day. All that quiz would have been on is the same stuff your simple harmonic motion assignment is on. That's redundant. We'll just not do it. Yes. Oh, you need the sheet, right?
Yeah.
I actually posted an electronic version of it as well.
What?